Hi, this is Dr. S. P. Asaf from Mechanical and Engineering Department, IIT Roorkee. In the course of vibration control, we are mainly discussing about the principles of active vibration control, in which we discussed about the basics, what the basic principles are there. Also, we discussed about various materials which are being involved like in active vibration control, in which you see here with the using of these smart materials or intelligent materials, we can say that we can achieve whatever the required purpose is there for the active vibration control, means whatever the vibrating masses are there, that can be straightway suppressed out with the using of these smart materials. So, we started from this piezoelectric materials, then we discussed about the ER, the electrorheological fluid, magnetorheological fluids. We also discussed about the electro and magnetostrictive materials, and in that you see here we discussed about the shape memory alloy, which has some anthropomorphic these features are there in their material, even up to the plastic nature, means plastic deformation, they can be recovered themselves into their original shape. And then in the last lecture we discussed about the spatial featured the electromagnetic dampers, and we found that you see all these, right from the materials to these these devices, they can be straightway act as the damper, means you see they can added their viscosity by adding this magnetic or electrical fields, or even you see they can even sense those part, and then they can go towards the actuation part. So, the meaning is very simple. From these materials or these we can say the devices, or the integration of the sensor, actuator and the control unit, we can suppress the vibration by introducing the force or the damper or anything like that. So, we discussed you see the two broader categories in entire vibration control mechanism, the passive vibration and active vibration. We solved some of the numerical problem based on you see the insertion losses, and you see what the impedances are there, what the mobilities are there, and how we can design effectively the isolator or the absorber against the continuous loading or the shock loading. So, today you see we are going to discuss about the second part of the numerical problems in the active vibration control. So, here you see we have the first problem, which simply indicates that absolutely based on the this wagon part, in which you see when the train is moving, we know that even at the lowest frequency we have you see the huge vibrations which can be even transmitted to the platform, and there is a huge noise together. So, we will just try to formulate the problem, that you see what exactly the things are being there and how we can resolve the issues. This problem is mainly taken from the standard book which was adopted for the entire course development under the MOU between the IIT Roorkee and the KTH Sweden, the fundamentals of sound and vibrations by the KTH book. So, if you will see that this problem, it is just saying that to achieve the good vibration comfort when we are boarding a train, it is important to limit the bending oscillation of the wagon carriage body. So, you see the entire carriage body, when we see that we just want to control the vibration, there is one mode in which you see the bending operations are there, and at the lowest frequency, if you are saying that the eigen frequency, rather the natural frequency is F1, which corresponds to this bending mode shape. So, now you see here when we are just trying to see that what kind of the bending these wagons are there. So, if you are saying that this is what you see my wagon is, and in this wagon, in this part you see here, if I am saying this is the wagon part which has some mass say m, and when you see it is in the mode of say the bending part. So, we can say you see this is what you see the kind of mode shape which can be there in this part. So, this is I am saying that you see when the oscillations are there in that part, this oscillatory feature is there, we can say this is you see the bending mode. And in this bending mode you see here the entire wagon is absolutely, when it is oscillating, you see the entire wagon is in this particular phase in which you see it is being oscillated. When we are saying that this is being attached to say this is what we have the bogies. So, this is you see the bogie part is there, and this is being the mounted feature of the bogie, and below the bogie we have say these our wheels are there. When I am saying that, you know, like this is the rails on which you see these, you know, like the wheels which are being moving. So, say this is absolutely, you know, like grouted towards the, we can say, the suspension system there in the soil or something, you see. So, this is, you see, the entire part in which we can see that, you know, like these bogie part is absolutely being attached there, in which you see we have, you see, you know, like both the kind of suspension that this primary suspension system and the secondary suspension system is there, and this is, you see, you know, like this is what you see our problem, and we are saying that this bending mode is occurring at the lowest lowest exciting frequency, we can say this F1. So, this mode which corresponds to, you know, like we can say the lowest frequency is absolutely with the bending mode. So, we have, you see, this bending mode. Now, we are trying to resolve that. This is, you see, the exact configuration of this problem. Now, we want to suppress this one. So, when we want to suppress the vibration which is being there, you see, you know, like creating by this movement under, you see, the bending mode of oscillation, then we can say one of the possibility, even in the question it is given clearly, one of the possibility is to use the heavy transformer as so called the resonant absorber. So, in one of our lecture we discussed that if you are adding, say, attached mass or the seismic masses, then we can reduce or we can suppress the vibration. So, here in the question they are saying that one possibility which we can use, you see, as a vibration absorber is the heavy transformer, or we can say some added mass is there, and the resonant this resonant damper will minimize the vibration in the this chassis, wagon chassis, and in exchange the absorber, that is, you see, the transformer will oscillate with the large amplitude. So, you see here in like either of that, you see, when we are talking about this. So, now if you are going back to our system, we know that now we need to add a kind of, you see, you know, like the transformer. So, we can say this is what my, you know, like the transformer part, in which you see the spring and you see this damper is there, and this is being attached to a mass. So, if I am saying this is my mass M1, I can say this is my mass M2, and you see here these spring dampers are there. So, this is what my, we can say, the absorber, vibration absorber, this vibration absorber, or we can say this is nothing but equals to the heavy transformer. So, this heavy transformer is being now attached, you know, like with this we can say the bending mode of oscillation, and this below part, there we can say that by adding these things can we suppress with the use, can we suppress the vibration with the using of the spring and the damper. So, now you see here this is, you know, like this our entire part which basically we would like to discuss in our question in this. So, this is what our problem is, you know, like again you see here we can repeat out this problem. What we have, you see, you know, like a kind of wagon this carriage body which is under, you see, you know, like the bending mode of oscillation, and in that you see here when it is being, you know, like operating under this situation where the bending mode of oscillation is there, we can say we have the exciting frequency F1, and then this lowest exciting frequency can be, you see, you know, like absorbed with the using of this heavy transformer, which we are saying that the resonant you know, like this absorber, and then you see, you know, like the entire things are there. So, now you see here, now we would like to put this into, you know, like the spring mass damper system. So, if you look at this part, we have the same situation here, the exciting frequencies are being there, you see, you know, like the exciting forces are there, you see the F. Now, this M1 is the mass which we discussed about the wagon part. So, this is my entire wagon. This wagon is basically associated with the two, we can say, the bogies part. So, this is, you see, the bogie where the suspensions are coming. So, you know, like the suspension, we are saying that this is, you know, like the symmetrical feature, absolutely, you know, like arranged in a perfect way. So, we can say the K1/2 and K1/2, the suspension is coming from the bogie part. In between, when we are saying that we have the heavy transformer, or we have, you see, you know, like the resonant damper, we can say this part which is used as the absorber have mass M2. This has the mass M2, and you see whatever the spring and damper features are there, we can say it is K2 and dV2. Now, we know that when this is being excited, the entire things are being excited, say it is a 2 degree of freedom system, because one mass which is the entire wagon mass is, you know, like moving with the Z1 oscillation, that is what my displacement feature, and M2 mass is being, you know, like we can say oscillating at Z2. So, this is you see like we can say the model of the wagon with the absorber in the spring mass damper feature. Now, we would like to like again go back to the question. They are saying that in the frequency band surrounding to exciting lowest exciting frequency in the bending mode F1, the system can be modeled as the 2 degree of freedom system as we discussed there, where M1 is the model mass of eigen mode shape connected with this part, and the K1 is the spring rate chosen such that the mass spring system without the resonant absorber would have the same eigen frequency as the this wagon body. That means you see we are saying that whatever the foundation which we have is a rigid foundation, and clear transformation, the transmissibility is there from that, and that is why you see here we can simply put the analogy as K1 by 2 and K1 by 2 in both the side. M2 is the mass of transformer which is simply being acted as the absorber. dV2 which we need to add towards you see the transformer feature. So, it is the viscous damping coefficient with the transformer suspension, and K2 is the spring rate for the transformer suspension. So, we can say that you see the transformer which is absolutely unlike if it is we are saying that the transformer is just suspended undamped part. So, we have only the spring, and if we are saying that no, this is the entire suspension features are there against the shock absorbing feature, then we need to add the damping and the spring together. The F is the excitation force, and we know that when the train is moving, it is absolutely we have the bending mode oscillation, and the responsible figure for that is the capital F, that is the excitation force. So, these all the parameters which is being there you see in formulation of the problem. So, when we are saying this is like the rigid foundation is there, so we can say that you see for undamped feature we have K2 and M2 only. That we can straightway say that if it is being acting only at the undamped part, no shock absorbing is there, we can use the spring as you see one of the suspension feature with the added mass like for heavy transformer. Now, the question says that if the wagon has the length L and the total mass M is there, when we are just excluding the transformer, then it is being fixed to the bogies in the simply supported manner. That means you see here now we are saying that if the added mass is not there, then initially this entire bogie can be treated as the single mass M with the length L, and you see here since it is being supported at the bogie part the entire wagon, we can say that this can be treated as this we can say simply supported beam. So, this is what you see, the two supporters are there from the bogie. The entire mass is being since it is a rigid foundation, they are simply we can say exactly joined at these point, and this is the entire we can say the length, and they are just moving in the forward direction. Say the x is the degree of freedom in which the movement is there. So, when we are considering this configuration without adding the mass, we can say this total M1, the model mass is nothing but equals to the entire you see whatever the distribution of the mass is there with the mode shape. So, this 0 to L integration phi 1 square K1x into M by L into dx. So, this is you see one of the simple configuration when the distribution of mass is there along with the this mode shape, where phi 1 with this phi 1 K1 comma x is nothing but equals to sine, because it has a sinusoidal feature because the excitation feature is also the periodic nature. We can say phi 1 K1 x is nothing but equals to sine of pi by L into x. So, it is a variation. So, we can say this phi 1 K1 x is nothing but equals to the relevant eigenvector. So, now you see the question says that we need to find out the modal mass M1, the spring rate K1 and K2, and we need to express these in terms of the parameters, that is M1 and F1 is there you see accordingly. Set up the equation of motion in the matrix form. That means you see here we need to find out the mass damping stiffness matrices with the force part in the we can say the matrix formation. So, we can say we need to use the state space variable and we need to find out that. The third part saying that suppose the lowest frequency is F1 which we discussed, and at that frequency you see the peak amplitude of the displacement A of M2 means the mass transformer, at most we can say it is a 10 times those two M1. Then we need to find out you see what the K2 and dV2 is there when the transformer mass is 5000 kilogram. So, you see here there is one condition where we can say that the peak amplitude of the displacement of the added mass, or we can say the transformer, is maximum is the 10 times of the even the mass M1. Then what are the values of these K2 and dV2, the associate damper, and you see the spring this spring rate when the total the mass of the transformer which is m2 is 5000 kilogram. So now we are starting the problem. So we need to first go that you see, since the model mass m1 is supposed to be determined, so for that we need to just go that what exactly the configuration is, and in the question it is clearly given that the entire mass m1 is distributed all across the two wagons or two bogies. So we have the two supported which can be acted as a simply supported beam. So you see here the simply supported beam starting from x equals to 0 to x equals to 1, x equals to L. So this is the total length is given to us, and we know that the exciting part is in the bending mode. So at the frequency f1 we have, you see, the mode shape is phi 1, the psi 1 which is nothing but equals to the sine of k1x. So we have, you see, this is what you see the lowest mode of the entire bending, which is clearly showing that you see, like this is the bending mode of this part. And then when we are showing these things, we can simply find out the lowest bending mode of these, like railway wagon with the using of this psi 1 is nothing but equals to sine of pi by L into x, or we can say this pi by L is nothing but equals to whatever the deforming feature is there, we can say it is nothing but equals to sine of k1 into x. Now we know that we can straightway find out that what is the modal mass is there of the entire wagon. So m1 is nothing but equals to integration, which was given in the question also, integration of 0 to L phi 1 square k1x into m by L dx. We can put this phi 1 as sine of pi by L into x. So we can say that even it is simply integration of 0 to L, means the integration of the total length where you see the mass is being distributed in the wagon. So integration of 0 to L sine square of pi by L into x into this m by L into dx is given. Now we can convert this sine square into cos of 2x, which is nothing but equals to 1 minus cos of 2, like we can say x divided by half. So when we are keeping this, we know that it is nothing but equals to m by 2L, which is the constant features, m is constant, 2 and L is constant, we can take out of them, and now we can integrate the entire features where you see the mode is being, like the entire molecule or entire fibers are under the this bending mode is there. So we can say it is integration of 0 to L 1 minus cos of 2, now 2 is there, cos 2L is there, so cos of 2 pi x by capital L into dx. And when we are integrating this, and when we are putting those limiting values 0 to L, we know that this m1 is nothing but equals to, m1 is the modal mass of wagon, so it is nothing but equals to m by 2. So we can say the modal mass of wagon m1 is the half of the mass of the total wagon part. So when we are just trying to find out that what exactly the modal mass is there under the bending vibration, we can simply make the configuration when it is being uniformly distributed all across the length, it is half of the total mass. So modal used here implies that the immediate vicinity of the actual frequency f, which is the lowest frequency, the distribution beam can be replaced by a rigid mass and the spring itself. So we can, when we are simply putting those things, we can simply find out that there is a clear analogy or clear representation of the entire beam and the spring features. So without going into detail of these things, we can simply say that when the point of departure at same, you see, means we can say at the same maximum amplitude of the two equivalent system, the kinetic energy of each system must be same, because we are saying that you see whatever the deflection features are there with the maximum amplitude, when they are, you see, just showing the two equivalent system, certainly you see here the kinetic energy should be same in that way. So to base our analysis, we can say that the displacement in this z direction where we were showing, you see, the rigid mass m1 or the beam part, you see here, we can get the displacement feature first. So the displacement for rigid mass which is being there on that is nothing but equals to, say if we are saying that the displacement, so this epsilon this m1, which is the dynamic parameters, the displacement is there. So it is epsilon m1 t is nothing but equals to epsilon, which is the maximum displacement, into sine of omega t. And when we are going for the beam, then certainly you see here the space coordinate, because you see it has certain the width is there. So we can say that for the beam, the displacement of the beam, epsilon beam, is x comma t, and we can say that you see here the mode shape will be coming together. So we have epsilon, which is the amplitude, into psi 1 of this k1x and then sine of omega t. So we can say either this epsilon into sine pi x by L into, we can say that, sine omega t. So, we know that the epsilon is nothing but equals to the maximum amplitude, and for the linear density m by L, because we know that there is no change in the like the homogeneous and the isentropic properties are being considered. So, there is no change in the mass configuration in the entire bogie. So, we can say the linear density is being featured out for the beam, and when we are saying that these things, then the kinetic energy can be immediately evaluated for the rigid mass and for the beam. So, first of all, for the kinetic energy for the rigid mass m1, we can say that the kinetic energy k for m1 is nothing but equals to half m1, and then you see here this entire displacement is featured out. So, it is d by dt of epsilon sin omega t whole square, and for the beam also you see here, now we can straightway put together the epsilon this k, and for the beam entire is nothing but equals to integration of 0 to L, because there is a clear you see like the space is also there up to the x part. So, 0 to L m by 2L d by dt of epsilon sin pi x over L into sin omega t whole square into dx. So, when we are formulating this, now we know that it is nothing but equals to, again when we are trying to formulate this, again we need to keep the two things together. One, when we are saying that you see like the sin omega t, and second the sine of pi x by L, because ultimately we are multiplying this into dx. So, you see here when we are integrating and when we are putting this, we have half of d by dt epsilon sin omega t whole square 0 to this whole square, and then integration 0 to L phi 1 square of k1 x into you see m by L into dx. So, you see here like this, we know that the mode shape is the function of dx. So, it is being there with the 0 to L integration, and you see since like we know that whatever you see the sinusoidal features are there, they are being epsilon sin omega t with the displacement. So, d by dt is there this. So, these two kinetic energies when we are just keeping together, so we know that like we can simply keep both the kinetic energy should be equal. So, m1 which is nothing but equals to 0 to L phi 1 square k1 x m by L into dx, we can say that we can find out the eigen frequency for the lowest this is lowest eigen frequency for the bending mode feature under this mass spring system with the m1 k1 is f1 is nothing but equals to 1 by 2 pi square root of k1 by m1, or we can say that m1 which is nothing but equals to m by 2, we can say f1 is nothing but equals to 1 by 2 pi 2 k1 over m. So, this is you see the eigen frequency even when we are keeping this with the stiffness part, the stiffness is k1 is nothing but equals to 2 pi f1 square m by 2, or else we can say that you see here the spring rate which is nothing but you see like of whatever the stiffness features are there of the resonant absorber can be get easily by f1 equals to 1 by 2 pi k2 by m2. So, we can simply show the k2 as 2 pi f1 whole square into m2. So, this is you see like we can say these values means these expressions, one where we have you see clear what exactly the kinetic energies are there. So, this is what you see the kinetic energy for mass m1, the kinetic energy for mass m2, what is the eigen frequency, eigen frequencies are like that, and we can get you see the spring rate or the stiffness like for the absorber and for you see the entire wagons wherever it is to be required. So, k1 and k2 can be easily get. The B part was there where we need to set up the equation of motion for given 2 degrees of freedom system, as we discussed you see where m2 which was there as a like the transformer, m1 was you see the wagon part is there, and then when we are starting from that you see when we have a rigid foundation and you see the entire beam part is there, we can simply find out that like this that how we can get those parameters means like the remaining parameters out of which. So, we know that it is a 2 degree of freedom system, we can straightway go to the equation of motion for that in the matrix formation. So, we know that the mass matrix must be symmetric all along you see the diagonal, because you see we know that m1 0 to 0 to m1. So, this is one thing is there, even when we are talking about the stiffness matrix, it is k1 plus k2 then minus k2 along this diagonal and then k2 is there. When we are talking about the damping which is only there with the mass m2, so we can simply spread in that way. So, when we are talking about this, we have now the equation of motion which was required you see here as minus omega square matrix m, and matrix m is this m1 0 0 m2 into you see the displacement. So, displacements are given as you see the z1p and z2p. this is what you see here, like the forced part is there because we are applying the force. So we have, you see, like the displacement for the particular integral under this is z1p and z2p plus iota omega. This is what my natural frequency into dv2 minus dv2 and dv2, because there is no dv1 as such, you see here. So you see epsilon 1p and this z1p and z2p is there, plus you see, like the k1 plus k2 minus k2 and the k2 is there. So we can get, you see, all these mass, damping and stiffness matrices with there, you see, like the mode shapes, and then this is what my forcing frequency f, the forcing force factor f and 0. There we can simply put m1, which is like m by 2, as we know that k1, as we discussed already, 2 pi f1 2 pi f whole square m by 2, and k2 is 2 pi f1 whole square m2. So we can keep and we can get all the things. The last part was there, which is like for a linear system, such as you see, like we are considering that whatever the ratio in between the amplitudes z1p and z2p is absolutely at, we can say, like just moving at the constant and independent of the peak amplitude for the excitation force f, then we can get, you see, the ratios of that, and we can get that what exactly, like the relative displacements are there of the masses of both m1 and m2 with these peak amplitudes. So again we need to go with the same equation, and we need to find out that what exactly the eigen modes are. So minus omega, you see, minus omega 1 square m2 z2p minus omega dv2 z1p plus plus iota omega, we can say dv2 into z2p, and then we can say minus k2, which was, you see, the stiffness of the mass m2 associated with the z1p plus k2, you see, z2p is equals to 0 when we are just trying to keep these systems in that way. So we can say that, you see, the ratio between the, like the mass amplitude z2p by z1p is nothing but equals to iota omega dv2 plus k2 and divided by iota omega 1 dv2 plus k2 minus omega 1 square m2. So this is all the, like the manipulations from the above equation. We can get this z2p and z1p, and when we are trying to do the square, we know that it is nothing but equals to the square k2 square plus omega 1 dv2 whole square divided by the k2 minus omega square m2 whole square plus omega 1 dv2 whole square. So this is, you see, like the individual factor. When we are just trying to evaluate those things, we can get this z2p by z1p whole square. Our intention is to find out, you see, that what is the dv2 here from that. So dv2 can be straightway calculated as 1 by omega 1 k2 square minus z2p by z1p whole square, whatever the amplitudes ratios are there, into k2 minus this m2 omega 1 square divided by z2p minus z1p square minus 1, when we are just trying to like model this square root of that. So we can say that when we are trying to keep this omega 1, which is nothing but equals to the natural frequency, the lowest natural frequency 2 pi f1, and when we are keeping this k2 as 2 pi f1 whole square into m1, then we are concluding this dv2 as nothing but equals to 2 pi f1 m2 divided by z2p minus z2p by z1p modulus of this square minus 1. And we know that, you see, here the first natural frequency is 15 hertz and m2 is, like given as 5000 kilogram, and we know that when the amplification, or we know that when this z2p is, like exciting 10 times than z1p, when we are keeping these things, we know that, like these numerical part will simply give you that dv2 is nothing but equals to 4.74 into 10 raised to power 4 this Newton second per meter, that is the damping value. And when we are keeping into our k2, which is nothing but equals to 2 pi f1 whole square m2, then we have, you see, the stiffness value, that is 44.4 mega Newton per meter. So this is, you see, like we have all the values, means when we are keeping the mass value and all, this is what the relations are there. With this relation, we can get all the value when we know the input values as like m2, f1 and z2 by z1. So this is numerical, this is something, like the numerical problem in which it is clearly showing that with the addition of mass as the absorber, how we can suppress the vibration, or how, you see, the other things can be, like evaluated with this. Now we are going to the another problem of this. In this we have a machine. You can see on your screen the machine is there, in which, you see, it is simply moving not only in the vertical direction, but also it is rotating. So now we have it is like because the two springs are there, so it can oscillate to and fro part, but also you see here it can rotate, as you see like like the junctions are there at which you see it can rotate. So we have you see like the moment is being there which is being excited, and the force, and this force is not you see like passing through the center of the machine, this centroid feature or the center of mass, it is like the eccentric feature, and this eccentricity can be measured as A into zeta. Now suppose the foundation is rigid, so now you see there is no deforming features with the foundation part, and the machine is to be elastically mounted at two mounting position, as you can see K1 and K2 are there, 1 and 2. The figure shows that in this that there is a like the mechanical model of an elastically mounted machine with 2 degrees of freedom, where you see the vertical translation, the translational feature and the rotations are being considered. The key feature is that this rotation point and these two elastically mounted features are well balanced, because A and A distances are there from this point. As you see like as it is moving, so we may have you see the kind of like first mass m1, and second is the moment of like inertia, the j is there to gather this. So machine is symmetric. We know that because you see it is absolutely no, because if we are not considering symmetric, certainly we would have the unbalance or some kind of misalignment can be there because of this rotation or translation. We can say it has mass m1 and the mass moment of inertia is j. Both elastic element can be regarded as the ideal mass spring. So we are not considering any mass, as generally we are considering like in other part with this stiffness. So we have K1 and K2 are the spring rates at this, and if we are saying that during the operation whatever the motions which are being generated, they are equivalent to those generated by this force excitation. So we are now putting the analogy that during operation this much mass and the moment can be generated. So this is, we are saying F excitation and M excitation is the force, the excited force and excited moment together. The force is applied at the distance A, zeta you see here, from the center of mass, and the harmonic force which is being like excited is F is nothing but equals to F E I omega t, and M is nothing but equals to M E I omega t. This is all harmonic excitations are there, so we can be featured out this one. Now the question is, now we need to find the expression for the spring forces F1 and F2 which are being there at these two location of the spring at these two. So here F1 is my restoring force, F2 is my restoring force at these two locations 1 and 2. So we need to find these F1 and F2 which are being exerted from the foundation on the foundation, in if the first condition is the zeta is 0, and then you see here this F excitation and M excitation is not equals to 0. That means you see here this excitation features are like being acted there, the zeta is 0 there. Second, the zeta is 0, and then K1, K2 and K, the spring rate is constant from both the side at 1 and 2 like with the rigidly mounted on the foundation, and we do not have you see F excitation and M excitation is not equals to 0. The third case is when the zeta is not equals to 0. Again remember the zeta is nothing but A into zeta is the linear distance where the this F excitation is being acted. So zeta is not equals to 0 now, but a spring rate K1, K2 and K is equals, they are equal. F excitation is applied it, but there is no moment. So M excitation is 0. So these are the three conditions which we are going to apply to formulate F1 and F2 spring rates. B part, we need to calculate the insertion losses, where you see the several alternative approaches like are conceivable. In principle, if you are talking about the insertion losses, they are indicating the change in some of the quantity of the interest with the dimension of power, and at some particular point, due to the presence of vibration isolator, we know that there are you see like some kind of you see the insertion losses. So in this case we can say that there are two contributions to take into account, and we need to compare both the features like in case of this A, and we can say in which you see the third case where we have like the eccentric force is there and the spring rates are same, but there is no moment is there. So in this case now we can say that the two main conditions are like this. First, suppose the effect of vibration isolation is described by the insertion loss with regard to the total force, which is the linear summation of both the F1 and F2 exerted on the foundation. So we can find out the insertion loss, which can be straightway derived, DIL is nothing but equals to 10 log of this F square total without like applying this isolation divided by f square total with isolation. Second solution is the alternative would be make the use of summation of the mean squared forces, whatever you see the forces which are being coming, and the definition of the insertion losses can be of DIL tan log. Now the like since the insertion losses being coming out featured out from the square of this the mean square forces, so it is f1 square plus f2 square without isolation divided by f1 square plus f2 square with isolation. And then you see here we need to find out that how we can get those things. So first, the first condition says that we need to find first f1 and f2 for these conditions. So in that we can say that when like the degrees of freedoms are being increased, we know that the complexity in the solving problem is more of like this increased. So first we need to say that we have the two main coordinate system where the movements are there. One is the translational, we can say you see x1 and x2 are there because of m and j. Second is the rotation, so xg and this theta g is there for the rotational features. The first case was there where the zeta is 0, but f excitation and m excitation is present there. So now you see here when we are applying this and you see like when the oscillation and the translational features are being there together, the equation of motion first for rotation part is nothing but equals to j into theta j double dot, the inertia force during the rotation, equals to f1a minus f2a, the distance of a, like from k1 and k2 are same a distance. So the moment from this is coming f1a in one direction and f2a from other direction. So f1a, when the forces being acting from the distance, they are absolute in the same direction where the m excitation are there. So we can say the total moment on this side is f1a plus m, and then the like the reverse direction is minus f2a. So the equation of motion is j theta g double dot is equals to f1a minus f2a plus m excitation. Now if you are going towards the other dimension, that is x, so we have m into xg double dot, that is you see the inertia force due to like the linear motion, equals to, now you see in the restoring forces which are being like the opposing part, so it is minus f1 minus f2, and you see the other part, the spring force which are being acted on topward, the forces which are being there f excitation on downward, so plus f excitations. So now we can say that this f1 and f2 is nothing but equals to k1 x1 and k2 x2, where x1 x2 are the linear, we can say displacement, and k1 and k2 are the spring rate, or we can say this is nothing but equals to our stiffness features of this spring, corresponding springs. And also we can say that the x1 is nothing but equals to, when we are just making the displacement feature linearly, so x1 is nothing but equals to xg. So first at xg, whatever the displacement of the g factor at the g point, the gravitational point, and then you see here minus theta g into a, because the distance is a here, so theta g whatever the rotational into a. Similarly x2 is also same, but only the direction is difference here, so we have this xg plus theta g into a. So these you see the linear summation in between like x1 and xg, x2 and xg from the this translational and the rotational coordinate. We can keep you see like these kinematic relations together in that way. The xg is nothing but equals to x1 plus x2 by 2, and theta g is nothing but equals to x1 x2 minus x1, what is the difference, divided by 2a. And we know that this is the harmonically time dependence problem where the time derivatives are being replaced by our frequency minus omega square. So we can say like when we are keeping those equations together, we know that with the using of the Hooke's law, our equations are now become minus omega square j by 2a f2 by k minus f1 by k. That is what my displacement features, and when we are multiplying with this equals to a into whatever the distance a into f2 minus f1, that is what you see the total difference of the moment is f2 minus f1, the resultant force, into a, that is the moment, plus m excitations. So you see here when we are making balance of these things, we can say that under the Hooke's law, this moment balance equation is clearly giving that what exactly the rotation is there when the moment is being applied and when the force balance conditions are like that. So we can say with this particular equations we can get minus m minus m by 2 omega square into f1 k by f plus f1 by k1 plus f2 by k2 is equals to minus f into minus f1 minus f2 plus f excitation. This is, you see here, the moment and the force balance conditions. When we are equating both the equations, then we can have, you see here, A minus this f1 is nothing but equals to the force f1 which we need to calculate is nothing but equals to, you see, this A minus omega square j by 2 k j by 2a k2 divided by A minus omega square j over 2a k1 divided by 1 minus omega square m by 2 k1, and this, you see, whole is coming from, you know, like as the just denominator 1 plus 1 minus omega square m by 2 k1 divided by 1 minus omega square m by 2 k2 into A minus omega square, same, you see, on the top of that, you see the same here, A minus omega square j over 2a k2 divided by A minus omega square j over 2a k1 f excitation. So, this is, you see, this part is coming from the f excitation, and similarly, you see, this m excitation features are also being there. So, this is this part minus 1 over 1 minus we can say 1 plus this is, you see, 1 minus. So, it is, yeah, A minus omega square j over this 2a k1 into 1 plus 1 minus omega square, we can say m by 2 k1 and 1 minus omega square m over 2 k2 into now A minus omega square j over 2a k2 divided by A minus omega square j over 2a k1. So, this is, you see, you know, like with the coefficients with respect to omega square m and k, we can simply calculate using f excitation and m excitation features. And similarly, f2 can be also evaluated using these features, 1 by this into f excitation plus this 1 minus omega square m by 2 k1 and 1 minus omega square m by 2 k2 divided by this into m excitations. So, this is what you see, the first condition where both, you see, the this f excitations are being there, both are being, you know, like present their case. Now, when we are saying that the zeta equals to 0 and k1 k2 are equal, means the stiffnesses are being equal now. So, we can keep the stiffnesses there equal, and you see both this m excitation and f excitations are being present. So, we can simply get, you see, you know, like in this f1 and here f2, when we are keeping this spring stiffness constant same or spring rate same, we can have f1 is nothing but equals to f excitation divided by 2 times of 1 minus omega square m by 2k minus m excitation divided by this 2 into A minus omega square j over 2 a k. So, now you see the k is same here, and similarly we can calculate the f2 as well, the f excitation divided by 2 into 1 minus omega square m by 2k plus m excitation 2 into A minus omega square j over 2 a k. The third case, in which you see here we do not have, you know, like the zeta equals to 0, it is the zeta is present, but the moment is 0 here. F excitation is there, spring rate is same, but there is no moment. So, the machine is now excited by the force only. The line of action at which you see it is being located, which is absolutely at the distance of this, you know, like x into a from the center of mass, and we can say now, you see here, this you know, like m excitation which was being calculated in the previous part is now being replaced by the f excitation into the distance, and this distance is a into zeta, because zeta is now present here. So, this is the total moment which is being acted by the applied force. So, when we are now calculating this part, we have f1 is nothing but equals to f excitation divided by 2 into 1 minus omega square 2 m by 2k minus, now instead of m excitation, now we have this f excitation zeta into a divided by 2 times of a minus omega square j over 2 a k. Or else, you see, when we are putting the manipulation, we know that f excitation is common in both the case. So, f1 is nothing but equals to f excitation divided by 2 into 1 over 1 minus omega square m by 2k minus zeta over 1 minus omega square j over 2 a k. So, this is what you see the features are, and in the second case also we can simply calculate, you see, when the first part is coming that both the forces f1 and f2 is they are being there without isolator. So, we can simply calculate, you see here, in the equilibrium position, because we need to derive the equations where, you know, like the f1 f2 are there, you know, without isolator. So, we can say the equations are the j into theta g double dot, that is the inertial forces during the rotation part, is equals to f1a minus f2a plus m excitation, where now we are saying that this is absolutely equals to theta z equals to 0 there. And this x double dot means m into xg double dot equals to minus F1 minus F2 the reactive spring forces plus F excitation, where you see here xg double dot is 0. So when you see we are saying that there is no isolation features, these are being there, and when we have like when we just want to solve these things, if m excitation is zeta AF excitation, we can say F1 is nothing but equals to 1 minus zeta F excitation divided by 2, F2 is nothing but equals to 1 plus zeta F excitation divided by 2, and then we can calculate the insertion losses by keeping 10 log like this F square this total without isolation and F square total with isolation, we can get these things. This is nothing but equals to 20 log 1 minus omega square m by k. So we can calculate, you see here the insertion losses in those things when we are keeping those values there, ultimately we are ending with DIL is nothing but equals to 10L 1 minus zeta square F excitation square by 4 plus 1 plus zeta whole square F excitation by 4 and divided by this whole is there, or else we can say that this is nothing but equals to 10 log 1 plus zeta whole square divided by 1 minus omega over omega square into whole square plus 1 minus omega square by omega r square this equals to like we can say the entire whole square, where omega 1 square is nothing but equals to we can say 2k by m and omega r is nothing but equals to 2a square k by j. So these are, you see, the rotational frequency and the translational frequencies are there, which can be straightway put it together just to represent that how you see these analogies are there. So this is what the expressions are, and we can get that. So in the last numerical now we are taking one more example in which the machine is now mounted on like the vibration isolation spring, and we are saying that you see like the vibration is simply being spread it out to the foundation and give rise to the sound pressure level, because you see here this is just the like the absorbing and releasing features are there. So we can store the energy, and when the expansion is there it is being released, no absorption, no dissipation features are there. And a frequency analysis which we can say like we just want to describe these things, it is at 25 hertz rotational frequency of the machine, which is like the main problem that you see at when the machine is approaching up to this, the huge amount of you see the sound, or we can say the vibration levels are being there. A reduction of sound pressure level by 10 dB at this frequency would be the required one. One of the possibility now here which we can say that to increase the mass of machine with the add of some additional weight, provided that the spring can be handled to increase the static load, and how much should be the mass to be increased to obtain the desired improvement, so that the 10 dB sound can be reduced there itself. You can see that this is what you see the vibrating machine, which is a very common machine, and it is like absolutely at 25 hertz. The huge amount of you see like the sound is being there, and it is being transmitted straightway to the ground and the surrounding. The original mass is 750 kilogram, and the eigen frequency of the original mounted setup without any additional mass which is supposed to be there is 10 hertz. So you see we know that the first eigen frequencies are there, but when they are approaching up to 25 hertz, then the things are more disaster. The machine including the added mass can be regarded as the single rigid body, because the added mass is like supposed to be act in the integral part of this machine, and the vibration isolator as the massless spring is considered, and the foundation is rigid, because we know that you see like the things are being transmitting in a speeder manner. So certainly it is there, the foundation is rigid. Now we are going, you see, we just want to find out the vibration amplitude of the entire you see candelier, which is to be reduced to the factor by 20 dB at an exciting frequency of these hertz. And you see here, because the system is regarded as the linear and corresponding reduction by the factor of 20 when these amplitudes are there, we can say the DIL, the insertion loss, is greater than equals to 10 log 20 by 1 square, or we can say 26 dB. So this is what you see the insertion losses when they are exciting at their own frequencies. According to this, now we can say that we can straightway put the shielding isolations there, and after the like entering the required input data, we can simply find out like that what exactly the stiffness parameters are there through which we can calculate this. So we can say that 26 dB, which is like generating at the insertion losses, is equals to 20 log 1 minus 2 pi the exciting frequency 5 hertz divided by k over 150. So we can say that you see to have the positive isolation effect, we know that the absolute value of these function must be equals to 0, or we can say 1 minus 2 pi f whole square, like divided by k by 150 must be equals to 10 to minus 10 to the power 26 by this 20. And when we are trying to solve for k, the k must be equals to, because we have right now 150 into 2 pi f whole square divided by 1 plus 10 to the power 20 by, you see, we can say the 26 by 20, we can say it is 7066 Newton per meter. So when we want to see that the value of this should not be increased, means the value of the stiffness should not be increased from this part, we can say the insertion losses must be the 26 dB supposed to be met at this point. So you see here we can straightway relate that, like when we are keeping the isolator, then what exactly you see, the values of the stiffness, or we can say the damper, or any other things are there, so that we can met the insertion losses up to a certain sound level. So in this chapter we mainly discussed about the numerical problems. There were 3 numerical problems related to the system parameters, and when we are talking about, you see, that vibration isolation either by added mass or either by the spring part, or either by, you see, the damping part, what exactly the key features through which we can do this. So this is the last part of our this module, where you see the active and passive vibration controls are there, how we can achieve those, by adding the material, or by adding the spring mass damper, or even by putting, you see, the sensor actuators and the control unit, that we discussed. Now in the next lecture we are going to discuss about the last module, which is, you see, the measurement, that how the measurement devices are there, what are the basics, what are the sensing, and the, we can say the data acquisition systems are there, and when, you see, we are getting those signals, then how do we process the signals, so that we can say that this is what the vibration signatures or the vibration signals are there, and we want to control these vibrations. So measurement is also one of the important part in the vibration features, whether the concept or the control part. Thank you.